we are starting the next section, the order topology. There is a natural topology on any ordered set, and this section is about that. So let us start with an ordered set X on which we have the order relation less than some order relation. Now you take any two elements A and B in X which are distinct and say A is less than B. Then these two elements determine four types of subsets of X called intervals, and they are these. The first one is the set of all elements X in X such that A is less than X and X is less than B. This is called the open interval determined by A and B, where A lies on that side and B lies on this side. Next we have this other type of interval, and in this interval we have those points X in X such that X is greater than or equal to A but less than B. That means A is an element in this interval but B is not. In the one above, neither A nor B belongs to this interval. In this third type, we have those points X in X such that A is less than X and X is less than or equal to B. So this one contains B but does not contain A. And then finally we have this fourth type where we have those points X in X such that X is greater than or equal to A and less than or equal to B. So both A and B are present here. This is called an open interval, this is called a closed interval, and these two types are called half open intervals. You are actually already familiar with these sets in your system of real numbers, but this is in a general ordered set. Now with the help of these intervals, we are going to describe a topology, define a topology on any such ordered set X, and that will be the order topology. So this is the definition of the order topology on an ordered set. So again, let X be an ordered set with some ordered relation, and this is important, X has more than one point. X is not a singleton set. Now let B be the collection of all subsets of X of the following types. Actually there are three types, but I ran out of space. We will see what the third type of sets is. So let's see the first type. All open intervals in X. We have just now seen what an open interval means in X. So any open interval you can think of in X, they are all inside B. Next, all intervals of this type closed open, where A0 is the smallest element in X, which actually may not exist. If X does have a smallest element as an ordered set, then in this collection B, this type of intervals will also be considered, where on the left hand side you have that smallest element, and on that side the interval is closed, and on the right side you have some element which is greater than the smallest element. And then there is one third type also, and the third type of intervals is this. All intervals of this type, open A, closed B naught, where B naught is the largest element in X if it exists. Now let us again emphasize this fact that it may not exist. Okay, as an ordered set, X may not have a largest element. If X does not have a largest element, then intervals of that type will be missing from this collection B. Otherwise, if there really is a largest element B naught in X, then all possible intervals of this third type will be there inside B. Similarly, if X as an ordered set does not have a smallest element, then no interval of this type will belong to B, otherwise all of them will be in B. In particular, if X has neither a smallest nor a largest element, then the collection B will be simply consisting of all the open intervals. That's the entire thing about this collection B. Now it turns out that this collection B is a basis for some topology on X, and that topology is called the order topology on X. This, however, needs verification. How is it that it's really a basis? Now, in order to show that our collection B is a basis for some topology, we have to verify those two conditions that we have in the definition of a basis. The first of them says that if we choose any point X in X, then that X has to belong to some element from the collection B. X has to be inside that element as an element. Do not forget that the elements in the collection B are sets after all. They are intervals, but they are sets. Now, several cases will arise. Suppose we can find elements A and B in X such that A is less than X, your chosen X, and X is less than B. So X lies between A and B in this manner. Then obviously X belongs to this open interval A comma B, which is of course an element in our collection. So in this case, we are getting what we want, but there are other cases. But say this is not possible, that you are unable to find elements on both sides of X in this sense. Then that means otherwise either X is the smallest element or X itself is the largest element. Why? How? Say you are unable to find an element like small a on that side of X. What does that mean? It means that no matter whatever element you choose from your set X, that is not less than X. But not less than X means what? Then it has to be greater than or equal to X. But that makes X the smallest element of capital X. So that way, if no element on that side of X can be found, then X has to be the smallest element. Similarly, if no element on this side of X can be found, then X itself has to be the largest element. There is nothing larger than X. So let us take these two cases separately. Suppose that X is the smallest element. Then there exists an element Y in your capital X such that Y is greater than X. The question is why? That is because do not forget that we have imposed a condition on the set X that it should have more than one point, more than one element. So if you have X here, I mean X is already in X, there should be at least one more point. And that one more point Y, of course, is not X itself, it's different from X. But X is the smallest element. Then what should be the relation between X and Y? Y has to be greater than X, obviously, because Y cannot be less than X. X is the smallest. So that way, you have got another element Y which is greater than X. But now you can consider this closed open interval X comma Y. And this interval obviously contains X, but now this interval is also an element of the collection B, Y, because now in this case there is a smallest element in your capital X which is this X. So that is why this type of intervals are also inside B. So in this case also you have found an element in your collection which contains your chosen point X. And the other case is that your chosen point X is the largest element. If X is the largest element of X, then again this time also there exists an element set in X which is different from X because your set has at least 2 points. So besides your small x there should be another one. But this time the largest nature of small x forces set to be less than small x. But now you can consider this half open interval open z comma closed x, and that of course contains your chosen point x, and it now is inside this collection B because now there is a largest element. So in this case also you see that your chosen point X is contained inside at least one element from the collection. So the first condition for a basis has been verified for this collection B. And the second condition is left to you with this information that if you take any two elements from the collection B, then obviously each one of them is of one of those three types. Then their intersection is either empty or again another interval of one of those three types that we have in B. And from that, of course, it follows that the second condition for a basis is also true for this collection B, and as such this really is a basis for some topology on X, and that is the order topology on X. Now next let us see some examples in which we are going to see concrete ordered sets, and we will see what the order topology on them are. Example 1 is about the ordered set of real numbers, where we have the usual order relation on the set of real numbers. Now we know that as an ordered set, R has neither a smallest element nor a largest element. That is why if you think of this collection of all such intervals in this ordered set, then you have only open intervals, and that collection of open intervals generates the ordered topology because it's the basis. However, we already know that that same collection of open intervals also generates the standard topology on R. So here we do not get any new topology on R. The order topology on R coincides with the standard topology on R. In example 2, we consider the Cartesian product of R with itself, that means two copies of R, and we are considering this set with a dictionary order. That makes it an ordered set. Now before we say something else, let us change the notation from this to this. When you think of the elements of this Cartesian product, by definition they are ordered pairs, but because we are going to use them in making intervals also, so the notation can become confusing. That is why instead of the ordinary ordered pair notation, we are going to write x times y. In fact, while discussing Cartesian products themselves, this new notation has been mentioned before, if you remember. Now as an ordered set, just like R, this set also has neither a smallest element nor a largest element. This means that the collection, the basis for ordered topology for this set, this ordered set, will have only open intervals because there is no largest or smallest element. But what are those open intervals? How will they look? Let's see. So these are the open intervals. The order topology on R times R has as a basis the collection of all open intervals in this ordered set, which are just these. But note that the boundary points, that means the ends of the open intervals now, are themselves ordered pairs. Do you see why we have changed the notation? Otherwise you would have had to write a comma b here itself, and that creates a very confusing notation. But what is the condition that we need on the ends for an open interval to be considered a valid open interval? The left end should be less than the right end. Less than in what sense? Less than in the definition of the dictionary order. A times B is less than C times D. If either A is less than C and that's it, or A is equal to C and B is less than D. Now because this is geometrically the two-dimensional plane, so we can draw figures for these two types of intervals. Actually we are considering open intervals, but there are two distinct types. Let's see how they look geometrically. So the first type of interval in which A is less than C looks like that. What does it mean for A to be less than C? It means that the point A comma B or A times B, however you may want to call it, lies to the left of C times D. Whether this one is below this one or above this one, that does not matter. Simply this itself tells us by the definition of dictionary order that A times B is less than C times D, regardless of what B and D are. So this is that point. This tip of this, tip means this bottom of that line, of that ray, and the top point of this ray is this C times D. They are themselves not points in this open interval because it's open interval. And by the definition of dictionary order, what are the points? I mean, geometrically, where will they lie? Those points which are inside this interval, they should be greater than A times B. So all the points that lie on this ray exactly above this point, all the points which lie to the right of this point, those points, for example, some point here will also be greater than this point simply because it lies to its right. The fact that it lies below it has nothing to do with the order. So all these points which lie to the left of this C times D to the right of A times B, along with all the points which lie vertically above A times B and vertically below C times D. Geometrically, this is this interval in this case. But the other case in which A is equal to C and B is less than D is much simpler geometrically. It is this vertical line segment. A is equal to C. Okay, so here actually you have C which is just A. What A is, C is also just that here, a point. But B of course is less than D. So the real number corresponding to B lies below the real number corresponding to D in this figure. So in this interval, again the endpoints are not included. So it's a line segment geometrically whose endpoints are not to be considered in this interval. So all such intervals, when you consider their collection, they form a basis for the order topology on R times R with the dictionary order. And incidentally, if you actually consider only open intervals of this second type, they also form a basis for the same order topology. Next we have example 3 in which we consider the set Z plus of all positive integers with the usual order where 1 is less than 2, 2 is less than 3, that thing. And this time this ordered set has a smallest element 1. Now it turns out that the order topology on this set is actually the discrete topology. That means every set is open. Let us see how. You consider any positive integer n which is greater than 1, that means n is at least 2. Then n minus 1 is also a positive integer, and so is n plus 1 of course. Now you consider the open interval whose one end is n minus 1 and that end, right end is n plus 1. Because we are in the ordered set Z plus, this open interval actually is just the one point set consisting of n. But this open interval by the definition of order topology is a basis element in the order topology on Z plus. And so by definition is itself an open set, and that is why this singleton set consisting of n is an open set in the order topology on Z plus. We do not however have included the single number 1. That's a little separate. Separate means it's different because it's the smallest element. For that we consider this, the closed open interval 1, 2. That turns out to be just this singleton set 1. Note that this is also a basis element because 1 is the smallest element in this ordered set Z plus. So this singleton set also is open in the order topology. So we see that all one point sets, that means all singleton sets are open, and that is why every set is open. Why? Because any set is a union of those singleton sets which are formed by its elements, and any arbitrary union of open sets is open. That is how in this topological space every subset is open. So obviously it's the discrete topology. So you get nothing new, you actually get a familiar topology in the form of order topology on this space. In example 4, we consider the set X, which is the Cartesian product of these two sets, the set 1, 2 and the set of all positive integers. Because both these sets are ordered sets, we can use their order and think of the dictionary order on this Cartesian product. And as an ordered set with the dictionary order, it has a smallest element, and that smallest element is the ordered pair 1, 1, or in our new notation 1 times 1. Now note that every ordered pair in this set has its first coordinate equal to either 1 or 2. Now if it has its first coordinate 1, then it looks like this, 1 times n, where n is some positive integer. Let us give this a new name, an, and it can also be of this type, 2 times n, where the first coordinate is 2. Let us give this the name bn. Then we can write the elements of this x in this more simple notation, all the ai's and all the bi's. Actually, I should also draw a figure that will make the order even more clear. So this is how it looks. The smallest element is a1, then the next bigger one is a2, then a3, a4, a5 and so on. And all these a's are less than all the b's. So if you leave the sequence of a's and start with b1, then b1 is greater than all these a's. But then the next higher b is b2, then b3, b4 and so on. Actually, that itself is shown here. The smallest is a1, then the order increases like that. But the b's are all greater than all the a's, and then it increases in that direction. Now, in this dictionary order, just like the set of positive integers, we do not exactly get the discrete topology, although almost all sets are open here as well. But I mean, all singleton sets are open. But there is one singleton set which is not open. Let's see which one it is. And that one point set is the set consisting of B1. So the author writes, the order topology on X is not the discrete topology. All one point sets are open except this one. Let us first see how all other one point sets are open. Actually, it follows that same pattern that we saw in the previous example. The set consisting of A1 is open because that is this basis element, closed A1, open A2, because A1 is the smallest element, so this half open interval is a basis element. Similarly, the other one point sets are open because each one of them is one such interval. For example, the singleton set consisting of A2 is the open interval A1, A3. The one having only A3 is the open interval A2, A4. So like that, all the AIs form one point open sets. Actually, all the B's here except B1 also similarly form one point open sets. For example, this one is the open interval B1, B3, which is a basis element, and so by definition it's open in the order topology. But why is this not open? Well, it is not open because, say this is open, okay, what will go wrong? By the definition of an open set, when you are talking about a topology given by a basis, by the definition of an open set in such a topology, if you have a point in that open set, then that point should lie in a basis element which itself should lie in that open set. Now the open set, say we are forcefully supposing that this is open. The open set is this and the point is B1. So now I have to be able to find a basis element in the order topology which will contain B1 and will itself be contained inside this open set. Now, what are the basis elements in this order topology, on this set? Obviously, they are either open intervals or intervals of this type, because our ordered set has a smallest element but no largest element. Okay. Now, any open interval, if you think of, which contains B1 has to contain some AI. Why? That is because you cannot take the left end of the open interval to be some B itself, because it has to contain B1, right? Even if you take the left left end point as B1, then B1 is not inside that interval. So the left end point has to be some AI. But the moment you consider the left end point as some AI, then in that interval you have AI plus 1, and actually the other subsequent AIs, all of them. None of them, however, belongs to this set, because this set has no AI. So no such open interval which contains B1 inside of it can be contained in this. And obviously, if you, instead of thinking of open intervals, if you think of half open intervals of this type, then also, of course, none of them can be contained in this, because they will also contain AIs, at least one AI. For example, A1 will always be there in all of them. That is why this single one point set is not open. All other one point sets are open. So the fact that all other one point sets are open, that will actually generate many open sets. But because of this failure, the topology fails to exactly be the discrete topology. It is something else. And let me just end this video here itself. After this also there is that notion of subbasis. There is a natural subbasis for the order topology on any ordered set, but that we will see in the next topology video. So see you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.